hinge theorem. It's on page 234 of your book, theorem 512 also, but hinge theorem is its name. It's kind of like side angle side theorem of congruence, except the angles aren't congruent. So we have two sides congruent. So AB and DE are the same length, BC and EF are the same length, they're congruent. But we're told that one of the angles is bigger than the other angle, so they're not congruent. So in this case, this is the bigger angle, because that's bigger than this, which is the smaller angle. And the hinge theorem basically says there's a relationship between the sides in these pictures since the two sides are congruent. If these two sides weren't congruent and these two sides weren't congruent, the hinge theorem is irrelevant. All right? It has to have something the same in order to have a comparison between these triangles. So once we see the two sides congruent, we're considering the third sides, AC and DF. The bigger angle is opposite the bigger side, biggest side is opposite the bigger angle. So there's also the converse of the hinge theorem, which goes the other direction. So the hinge theorem itself, they tell us the angles relationship. This angle is bigger than that angle. The conclusion of the hinge theorem is this side is bigger than that side. The converse of the hinge theorem goes the other way. The converse would say this is the same as this is the same as this, and this is bigger than that, which means this angle is bigger than that. That's the converse. So if you're trying to conclude that the sides, one bigger than the other, that's the hinge theorem. If you're concluding an angle is bigger than the other, that's the converse of the hinge theorem. So make sure that you have those under control. So look at example 1. As a rider pedals a unicycle, how do the measure of angle A and the length of B change? What does this suggest about the change in the triangle? So you can see here the seat post of each unicycle is the same because it's the same unicycle. And the distance from A to the pedal is the same because it's attached, right? So this is a bar that's not changing, this is a bar that's not changing. So these are all going to be congruent. This piece is congruent to this piece is congruent to this piece. And this piece is congruent to this piece is congruent to that piece. All right. The third side in each case is length B, and you can see here the crank arm is here, this acute angle happening. As the pedal goes this way, we should expect that B is getting longer, right? And as we continue on this way, B is getting longer. So we have an acute angle, we have a right angle, looks like a right angle. We're not supposed to assume a right angle just for the sake of this. Let's just say acute right. Let's just pretend they put a right angle in there. Acute right obtuse. All right, so less than 90 equals 90 more than 90. So smaller, middle, bigger, right? So in each case, looking at B, that's short, that's longer, right? So the relationship as A gets bigger, B gets bigger. Can we all agree with that? Because again, we have the congruence of the sides happening here. The hinge theorem guarantees that happening, right? So this congruent to this congruent to this, smaller angle, smaller side, bigger angle, bigger side. Biggest angle, biggest side. So how do the measure of angle A and length B change? As angle A gets bigger, B's length gets bigger. What does this suggest about the change in the triangle? That's change in the triangle. So I don't know. The second part of that question doesn't make sense to me as far as what they're asking me for, but I mean, in essence, the change in the triangle is the third side length is related to the angles measured. So I think that that's sufficient to answer both questions, in my opinion. Call that one good.